Okay, good afternoon. Let us start our lecture. So, in the last lecture, we talked about Jordan distribution. It arises when what we're interested in is more than one random variable for the same subject. All right, so in other words, instead of one characteristics, we are interested in more than one, so maybe let's say two characteristics of a unit or a subject, and how these two random variables are behaved can be represented by Jordan distribution. So we talk about two examples, one for discrete case, and we also talk about continuous. So here is let's recall a Jordan PDF of xy. X takes the value between 0 and 1, and y takes the value between 0 and 2. So this is a continuous random variable because both x and y take values, infinite number of values within certain region. So in other words, we have over this region 1 and 2. So over this region, we have a non-zero probability density. So you can think of it as a three-dimensional picture with x, y are the two dimensions, and then the third dimension represents the density function. So you can think of it, something come out from this shade area. And the height depends on the function. This is the function. In other words, it depends on the location of x and y. All right? So, you can see that this function, all right, represents the density functions at a particular point. The point is for given x and y values. All right? And then how about outside this region? So it's otherwise. So outside this region, the PDF is 0. It's 0. Okay? So before we find this probability of x plus y greater or equal to 1, we try to check whether this is a properly defined Jordan probability density functions. In other words, we have to check two things. Whether this PDF, Jordan PDF, is always greater or equal to 0. So in this case, it has to be 0 otherwise. And how about within this region, is it positive or greater or equal to 0? And the answer is yes, because x are positive. Y are also positive. So this is a positive value. All right? So the second thing that we have to check is to make sure that, all right, integrate from over the whole real plane, the PDF. Okay, we can, okay, to do the double integration, we do it step by step. We do it one at a time. So you can integrate x first by integrating x first means that we keep the y fixed, treat y as a constant. So we just handle one integration variable, x. After you complete the integration, that means after you finish this part, all right, then there shouldn't be any x in the expression. You can only see y or just numbers, all right? Because after you integrate with respect to x, you shouldn't have any x anymore. So after that, this is just a function of y. So this whole thing is a function of y. So just do the integration with respect to y. Then here's the questions. Does it matter whether we integrate x first or integrate y first? Okay. In general, there may be some difference. But for this module or the function, the PDF that we work on, it doesn't matter. All right? So it doesn't matter whether you integrate x first or integrate y first. You should, if you do it correctly, you may get the correct answer. You should get the same answers. Okay? Whether you integrate x first or integrate y first, it doesn't matter. But, there's a but. But if you pick the right order, that means you integrate with something, or for example, integrate with x first, it may make the integration easier in that sense. All right? So, it's just like go from here to the door, I can just walk straight. I can also go up there, then come down. Yeah, still get to the answer. So, in other words, it may make some difference only for the computation, the complexity of computation. So in other words, it doesn't matter whether you integrate x first or integrate y first, but if you pick the right order, it will simplify your integration. All right, so what we are asked is to find the probability of x plus y greater or equal to 1. All right, so what we do is to figure out this region. That means this event, x plus y greater or equal to 1. All right, this represents a region in the R square plane. So what we have to do is to look at the boundary. The boundary is x plus y equal 1. Equal. All right, so x plus y equal to 1, so draw the line. In fact, it's much easier. Just pick some point, simple point. If you put x equals 0, then y equal to 1. So 0, 1. 0, 1. This point, x equals 0 and y equals 1, is on this line. All right. Of course, you can pick 0.5 and 0.5. It's also on this line. X equals 0.5, y equals 0.5. All right. But maybe make it easier. Just pick y equals 0, x equals to 1. So this is the point. So it's a straight line. So 2 points will determine the line. So this is the line. X plus y equals 1. All right. Then which region or what does this event or this x plus y greater or equal to 1, which region it represents? So we just check. For example, this point. This point is with x coordinate 1, y coordinate 2. So 1 plus 2 is bigger than 1. Therefore, this point is satisfy this inequality. So we are talking about this region. All right. So to find this probability, basically is that we try to gather all the density within this region. But majority of this region does not have any non-zero density. So it's equivalent to, we just look at this part, the probability or the density. We just grab all the density over this region because the rest are 0. All right. So strictly speaking, we are looking at trying to collect all the density. So we do the integration. All right. So now in my notes, I try to work on this part. All right. But if I work on this part, all right. So I say integrate. Let's say I integrate x first. Okay. So that means I fixed y. Fixed y. So fixed y, I try to integrate. Y fixed. All right. X is from this to this. So integrate from, what is the x value here? 0. What is the x value here? 1. So integrate from 0 to 1. But how about if y is here? Then you integrate from this point, to this point. All right? So what is the value of x at this point? Do you know? Learn from this equation. So when fixed x, so x equal to 1 minus y for given y. So you are integrating from 1 minus y up to 1. Now you can see that if I integrate x first, so I have to fix y. Then the limits, the integration limits, all right, are different. So it makes the integration more complicated. You have to divide this integration into two parts. One is to integrate this part, because under this part, the lower limit and the upper limit of the integration are the same. Then over this region, the lower limit and upper limit are the same. I mean, not are the same. You can use the same expression to work on that. So that's why I say that if you pick the order correctly, then it will make life easy. So now, let me integrate y first. Integrate y first. All right? Then that means I have to fix x. Then what is the lower limit of the integration? It is from, at this point, what is the y value? Y equal to 1 minus x. So I start integrate from 1 minus x. All right? Up to this point, what is the y value up to this point? 2. So I integrate from 1 minus x up to 2 for this expression, x squared plus xy over 3. Remember, x is a constant. We fixed x. Okay, after I complete the integration, you can think of it like after you integrate, you just squeeze this region onto the x-axis. Because I try to collapse all the y's. So squeeze all the y's so that the density will all fall here at this point. So then the line, the whole line, only from here to here, that will have non-zero density. So I integrate from 0 to 1 dx. So that is one approach to get the answer, which is different from what I gave in the lecture notes. All right? So what I just told you is that, if you integrate, all right, integrate x first, keeping y, you have to do more, because you have to separate into two regions. Why two regions? Because the integration limits are different over these two regions. But if I integrate y first, keeping x, fix x, integrate y, that means sum up all the PDF of the y for the same x, all right? Then the lower limit and the upper limit remain the same throughout the region. So I don't have to worry about doing two separate regions. After you complete the integration of y, that means now you collapse or try to squeeze all the density instead of over this whole y, you squeeze it on the point on the x-axis. All right? So then we integrate from 0 to 1, because now x is from 0 to 1 that have non-zero density. All right? This is not a good way. I mean, it's a little bit more complicated, and complicated in the sense that the expressions are more complicated. Think of it, if now for there are 4 integration limits, 2 for the dy and 2 for the dx. There are only 1 0 there. I love 0, right? 0 makes things a lot easier, right? So now I only want 0. If you go to look at my expression in here. So instead of working on this part, now I work on this part. So this is my integration. All right? I have 2 zeros in my integration limits. So what does it mean? It means after I do the first integration, then the expression may be simpler, not so complicated. So it reduces my chance of committing some silly mistakes. All right? So what I'm trying to do is that, okay, instead of finding the answer, I find the complement of the answer, which is the probability of that triangular area. All right. Now, if I want to find that probability falls in that area, I have to integrate over this region my PDF. So I integrate y first. That means I fixed x. All right. So I fixed x. So once I fixed x, my integration will be from y is from this point, which is 0, up to this point. So what's the y value at this point? It depends on the x. And because of this equation, because it's x plus y equal to 1, so therefore this point is just the y equal to 1 minus x. Y equal to 1 minus x. All right? So this is y equals 0, all right, referring to this point. Y equal to 1 minus x, referring to this point. So after I complete these integrations, then every density at this x value will be collapsed on this one. So you can think of it, you squeeze this using this. You can think of it, you have a one plane here, one plane here. Try to squeeze everything so that it's on the x-axis. Then now we try to squeeze again. This time, squeeze this direction. Try to squeeze, all right? So that everything fall on this point. Okay, so I integrate from 0 to 1. 0 to 1, all right? In other words, after your integration, so only this part, 0 to 1, has non-zero probability density. All right? The height coming from this plane will represent by your answer obtained here. So now I integrate from 0, x equals 0 to 1, because only this part have non-zero PDF. All right? So I hope it helps you to do your integration. All right? Now, so this is answer. All right. So I don't think I have to go through all this. This is just, you can, because it's doing one variable at a time, so it's just an integration of one variable. So you can check this out yourself. So the answer is 65 over 72. So I would suggest that you try to use a different way to get the answer, see whether you got the same answer. This is the correct answer, no typo. This is the correct answer. So you try different ways to get the answer. So make sure that you know how to do the integration. Okay, let's look at another example. So here we have the John PDF. All right, it's given by this formula, so long as x is less than x between 0 and 1 and y between 1 and 2. Okay, now we define a region, x between 0 and half and y between 1 and 2. All right, and what is the probability that the random variable xy takes the value within this region, A? So you can think of it like this, x, y, x between 0 and 1, y between 1 and 2. So it's this part for which the PDF is defined. All right. Obviously, this is bigger or equal to 0. The probability, the John probability density function is bigger or equal to 0. And you can check whether this is a properly defined PDF. All right. But we are asked to calculate this probability. So what is this A? A is x equal between 0 and half. So this is half. So x between 0 and half, and 1 between 1, y between 1 and 2. So this is the area that we are interested. So now here I have a question. Does the answer equal to half? This area, A, is just half of what we are given. So is the answer equal to half? If you are in doubt, is it half? remember, this is the area. And when we talk about probability, it means that we are talking about the probability density functions. So think of it, if the probability density function is everywhere the same, then you can talk about the area. All right, but now the probability density function is not uniform, not the same. It depends on x and y through this expression 12 over 13 times x times bracket x plus y. So they're not the same. So therefore, the answer is not half. All right, not half of the area. You have to do your integration. No shortcut. All right. So now the question is to set up the integration. All right. So it's equal to the John PDF integrate from 0 to half. I integrate x first. That means I fixed y. Remember, this is the region. This is the region I'm looking for. All right. This is the whole thing that the PDF is non-zero. So I integrate x first. That means I fix y, y value fixed. So I integrate over here. So the starting point is x equals 0. X equals 0. And then the limit, the upper limit is x equal to half up to this one. So I sum up all the density over this line. All right? So over PDF. After that, after you complete it, make sure that no more x there. No more x there. All right? Okay. Remember, y is a constant. So you just do the integration with respect to x. After that, all right, then you substitute 0 and half into the results and get the answer. So here it is. This is the expression with x equals 0 and x equal to half. Okay, how about the limits of y? Now after you finish this, that means you try to put all the density function onto this part. All right, so only this part with non-zero density function. So the y is from this point, which is 1 up to 2. So you integrate from 1 to 2. All right? So we complete the integration. So it's 11 over 52. We can also, so you can try this one. So how about if I integrate y first? Of this 12, 13, and so on, right? So what are the limits? So now I integrate y first. That means I have to fix x. So I fixed x. I try to integrate for fixed x. In fact, I try to integrate this part. Try to collect all the density over the line through this x value. All right, from minus infinity up to infinity. But we don't bother about this part and this part. Sorry, this part and this part. We only worry about this part. So this part, the y value start from 1 up to 2. So the limit is 1 to 2. After that, that means all the density here will be condensed on this part, or you can consider as condensed here. Then it's only this part with a non-zero density for x. So integrate from x integrate from 0 to 0.5. All right? So this is x times x plus y. So this is another way to do it. You should get the same answer. Okay. Now, so we know the John distribution and how to handle the John distribution. So now, suppose I am only interested in one of the variables. So I want to know about how this random variable, one of them, how it behaves. So I talk about marginal distribution. All right. And also, because we have two, x and y, so we also like to know what happens if the other random variable, let's say x, fixed at certain values. So how does the random variable y behave? So that is conditional distribution. So we want to know, you are given the John PDF, okay, which I write it in this form. So now what I want is x only. and y only. Not only that, I also want to know what happens to the x, all right, to the x given y equal to some value, fixed value. So how does this behave? And also given x equal to certain value, how does y behave? All right, so here's the definition. The marginal distribution is given by this. So this is very simple. Basically it's saying that, okay, for discrete case, I add up all the probability function with same x value, with the same x value. In other words, it doesn't matter what the y value is. So long as the x values are the same, that means whenever you see, let's say for example, I'm interested in 1, x equal to 1. So I'm looking at all this. So long as you see x equal to 1, then you get the f1y. It doesn't matter what a y value is. So you just add them up. Add them up. So that is the f of x value at 1. All right? So similar for fy. So of course, this is fx value at 1. So fx value at 2, you just sum up all the f of 2y. All right? So like x equal to 2, you get all the probabilities. So that is the definition of marginal distribution. For continuous case, instead of doing summation, we do integration. So we are talking about random variable x. So we look at the John density and integrate y. That means we try to summarize or sum all or integrate all the John density with the same x value. So we try to integrate out y. All right? So this is the definition. All right, let's look at an example. So 3.15. 15. Which one is 15? Oh, this is 25. Okay, so this is the John PDF. So we want to know what is the marginal of x. Okay, first of all, ask yourself, what are the values for, possible values for x? So, x has to be 0, 1, 2, 3, 4, 5. All right? So there are altogether 6 possible values. So can x, okay, what happens to x equal to 6? Okay, the probability of x equal to 6 is 0. Why? Because the John PDF does not have any non-zero values for x equal to 6. So we only have this 0, 1, 2, 3, 4, 5 for all these random variable x based on this John distribution. So the next question is, what is the probability of x equal to 0? So what we have to do is to add up all this probability. That means whenever x equal to 0, doesn't matter whether y is equal to 0, y equal 1, 2, 3, we just add them up. Add up all this probability. So the answer is 0.05. So we have worked out all these 6 probabilities. All right? Okay. So this is for 0, for 1, and so on. So this is the the marginal of x. All right. Make sure this represents a PDF. So in other words, you have to check whether the f of x is bigger or equal to 0. All the numbers are bigger than 0. Second, you have to check whether the sum equal to 0. The sum of the probabilities equal to 0. So it's yes. All right? And it's understood that outside this range, that means x cannot be negative. All right? When we say cannot be, means that the probability of x equal to a negative value or x equal to a value greater than 6, greater or equal to 6, is also 0. All right? So make sure you have all this. Now how about margin of y? So we just repeat, but this time we fix the y value and try to sum up all the probability, the joint probability function with the same y value, but with different x. All right? So this is for x equals 0. This is f0, 0. This is f1, 0. This is f2, 0. f3, 0, and so on. All right? So the answer is 0.22. So you work all this and summarize it into a table. So there are 4 possible values for y, and these are the corresponding probability function. Make sure that they add up equal to 1. All right? In fact, this is how we do it. This is the marginal of y, and this is the marginal of x. And all these numbers should add up to 1. All these numbers should add up to 1. And all these numbers, the joint PDF, also have to add up equal to 1. Okay, how about this example that we just discussed? So what is the marginal of x? And what's the marginal of y? Now, from the definition, marginal of x is equal minus, integrate from minus infinity to infinity, the joint PDF, we integrate our y. That means fixed x, 3x is fixed, and try to integrate the joint PDF with y. Is this correct? Huh? F of xy equal to this, so I substitute it. Is it correct? If no, what's wrong? Please read carefully. PDF equal to this one only over here. In other words, only valid when y is between 1 and 2. Not only that, there's another criteria, x. Can that apply to any x? Okay. Yeah, so integrate from 1 to 2. In fact, I break it into 3 integration. Minus infinity to 1, the joint PDF. All right, I don't write the and then the next one is 1 to 2, the joint PDF. And then from 2 to infinity, the joint PDF. All right, what's the joint PDF here? It's not this one. It is 0. Because the y is between minus infinity to 1. Okay, so it falls here. So this is 0. This one, yes, this equal to this. All right. And this also equal to 0. So basically it's boiled down to integrate from 1 to 2, the joint PDF. But there's one more thing that you have to make it clear. Is it true for all x value? No, because this joint PDF equal to this expression, x has to be between 0 and 1. So in other words, if x equal to 2, so f of x 2, I cannot proceed like this because for x equal to 2, yes, this is 0 because it falls here. For x y here is also 0. But for this one, even y between 1 and 2, so satisfy this part. But x is not between 0 and 1. Therefore, this one falls here otherwise, so it's 0. All right? So in other words, you have to look at the region for which the John PDF defined. All right? The definition is to integrate. Nothing wrong with the definition. This is always true. And the problem is, what is this John PDF? So you have to pay attention. The John PDF, okay, valid for a certain region. All right? If that's the case, you have to look at what is the y range and what is the x range. So the y range appears in your integration limits for this example. But it also explicitly you have to state when this what you have done is a valid computation. So for example, x equal to 2, then this is not 0. This part when y between 1 and 2, but x equal to 2, which does not fall in this region. So you cannot substitute this into here. So it's wrong. All right? So in other words, this working only valid when x is between 0 and 1. Okay? So that's for marginal of x. Similar for marginal of y, you have the same thing. All right? So that's the solution. So you can see that I state clearly that this is only valid when x is between 0 and 1. Then I do the integration, break this integration into 3, sum of 3. All right? From minus infinity to 1, and 1 to 2, and then 2 to infinity. Why I break it into 3 regions? Because over these 3 regions, the form of the John PDF are not the same. Or you can say the first one and the last one are the same now. Both are 0. So we only keep the middle one, 1 to 2. Then John PDF equal this one. And do this integration, remember, we're integrating over y with respect to y. Therefore, x is treated as a constant. All right, so treated as a constant. So we complete the integration. So this is the answer. All right. So whenever x is between 0 and 1, then the marginal distribution of x is given by this PDF. All right. Then, what is the PDF when x is less than 0 and when x is bigger than 1? Then it is 0. Why? Because for x less than 0, then the John PDF is 0. I don't care about what the y is because it lies outside 0, 1, so it's 0. All right. Remember, this is the region. This is the region for which the density, John density is non-zero. All right? So therefore, we are only, when x is negative, like for example here, minus 1. Over all this, you don't see any PDF. So of course it's 0. All right? Okay? This part, basically saying that I integrate from minus infinity up to infinity over this, and no PDF, the PDF is 0 here, no density. So it's equal to 0. All right? So remember, whatever you have, remember you also look at when this is valid, when the expression, the marginal PDF equal to that expression. When? It's only when x is between 0 and 1 for this example. Outside that, it is 0. Okay, so similarly, I can work out for the y. So for the y, same thing. I need to specify the range of y for which the working is valid. And then I integrate with respect to x. All right, and x range from 0 to 1. Because over x between 0 and 1, then the John PDF is given by this. Outside this 0 and 1 range, the John PDF is 0. So I complete the integration, and it's 213 times 2 plus 3y. And will be 0 when y outside this range 1 and 2. That means if y less than 1 and y bigger than 2, the marginal density is 0. Let me repeat again. Because we're talking about marginal of y. So in the expression, you shouldn't see any x. All right? If you still have some x there, that means something wrong. All right? So similarly, the marginal of x, all right, is a function of x, no y. All right? All right. Then, conditional distribution. So xy are two-dimensional random variables with the John PDF f of xy, and we can work out the marginal. Then the conditional distribution is defined as the ratio of the John distribution divided by the marginal. If you recall, in chapter 1, we talk about this. All right? We talk about this. Although it's not exactly the same, but it basically is that, okay, if you want to know how y behaves when x is given at a particular value x, all right, then what you have to do is look at the John distribution of x, y, and then divide by the marginal of x at that value. Of course, the definition only valid when the marginal is bigger than 0. It cannot be 0. You cannot have a divisor or denominator being 0. Right. Now, this is the definition. So suppose I got the John PDF, I got the marginal of x, so I divide and simplify it, I got the answer. So let me ask you. So, this expression, the conditional PDF, is it a function of x and y? Yes, it involves x and y. All right? It's different from the marginal of y. Marginal of y, this is a function of y, no x, because you already integrate out x. This one depends on x. All right? Of course, sometimes a special case you may not have an x, but in general there should be a function of x. Function of x, and not just x, that can be of any function of x. Of course, because it's talking about y, then it also involves y, a function. So it's a function of xy. Okay? But as a random variable, how many random variables are there in the conditional distribution? Y only, x only, or x and y? It's important that you have to understand. All right? So what do you think? Y only? Y is the random variable? Or x is the random variable? Or both x and y are the random variable in this conditional distribution? So the answer is only y. All right? Why? Why is that so? Because we already fixed the random variable x at this value lead to x. So x is not a random variable. It already replaced or have a realization. We have the value is lead to x. Only y is the random variable. And this expression will tell you the density of y. How dense is the y? All right. For a given x. All right. So this is the same thing, except that now we change is x given y. All right. So here. So the conditional PDF sets for all the requirement of one-dimensional PDF. So in other words, the random variable x, the PDF is about the random variable x, and it has to be bigger or equal to 0. And not only that, integrate f of x given y is it dx or dy? I want to show that this equal to 1, right? So it's dx, right? Remember, x is the random variable. X is the random variable. We are talking about the how x behaves when you have knowledge of y. Y equal to a particular value. So this is what we integrate with respect to x. X is the random variable. All right? So similar for the other one. Okay. So for discrete case, it's sum over all the x equal to 1. This one, the random variable is y, so sum over y is equal to 1. So for continuous case, all right, this is the random variable x, so you integrate with respect to x equal to 1. This is the random variable, which is y, so you integrate with respect to y and has to be equal to 1. Let me remind you one more time. Although I write it like that, but remember, this is a PDF. It may take different form, or maybe just tell you one form, but it's only valid for a certain region of y, for example. Then outside that region, it's understood that the PDF is 0. So in other words, there are two forms. One is the form given to you. The other is understood that it's 0 over the region for which is not defined, not covered by the given form. All right, and so I just rearrange it. Remember the definition of y given x is equal to the John PDF all right, so I just move this, multiply both sides, so it's equal to this expression. So you can interpret as the John PDF or the John probability function, x and y. You can think of it as it is f of x, the margin of x, then times the condition of y given x. All right? So f of xy equal to this times this, or equal to f of x given y times f of y. That means times, first of all, get the y first, and then find out x condition on y. All right? Of course, all this valid only when this quantity is bigger than 0. Okay, so now let's look at some example. So we have a simple experiment. Have a fair con tosses 3 times, and they're all equally likely. I mean, the head and tails are equally likely. So here, from this experiment, we have x and y. X represents the number of heads in the last flip. So we have 3 times. So this is one of the possible outcomes. So this is one of the sample point. This is another one. This is another one. How many sample points are there? 8. How to get 8? 2 times 2 times 2. Why 2 times 2 times 2? We apply this multiplication rule. There are 2 outcomes here, right? Head and tail. For each of these 2 outcomes, there are another 2 outcomes for the second one. So it's applying the 2 multiplication rule. Then for each of these 4 outcomes, you have another 2. So it's altogether 8 possible points. And they're all equally likely. So each one has 1 x probability. But what's my x? X is the number of heads in the last flip. For this one, okay, x equal to 1. How about y? Y is the total number of heads. 1, 2, 3. So this sample points will map to 1 and 3, with x equal to 1 and y equal to 3, because y represents the total number of heads, and x represents only the third toes, whether it's head or not. So for example, t, 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 all are tails. Then x equal to 0, because this is no head. And all the 3 also have no head, so it's 0, 0. All right? So now we are asked, okay, what happens if I know that x equal to 1? That means if I know that the last toes is a head, then what is the chance, what is the probability? How does y behave? Or that means the number of heads, the total number of heads. How does it look like? Okay? So in other words, we are asked y given x equal to 1, or you're looking at yx, all right? Y given x equal to 1. Given x equal to 1. And y, what are the possible values for y? So, y can be 0, can be 1, can be 2, can be 3. Okay, I don't know whether this will take non-zero over these 4 values. But how do I know 0, 1, 2, 3? Because it's from the John distribution. The John distribution, y is the number of, the total number of heads. 3 toes, the total number of heads is either 0, no head, like this case. Or maybe 1 head, maybe 2 heads, maybe 3 heads. So that is from the John distribution. But I don't know until I work it out. I don't know whether any one of these 4 values, maybe some of them are with a probability equal to 0. Then I can drop it. All right? Okay, so first of all, we have to get the John distribution. So here is how we got the John distribution. So I list out all the possible outcomes. This is the sample points in the experiment, and these are the corresponding values, and these are the probability for each of these sample points. All right, 1x for each. So now I can see that for x, only 2 possible values. So x equals 0 and 1. No other values. Y can be 0, 1, 2, 3. So I construct this table with x 2 values, y 4 values. So this 1, 3, x equal 1, y equal 3. So this value goes here. Any other 1, 3? No more. So this means that the outcome, all right, if you have head, then it goes this way. Okay, then how about 0, 0? All right, so in that case, it corresponds to this event, t. So this will go to this category. So the probability of xy equals 0, 0 is the same as saying that we have t, which is 1x. So that's why it's 1x here. Okay, how about x equals 1 and y equals 0? That means the last one is a head, but then the total number of heads is 0, and that's impossible. So that's why 0. You don't see 0, 1 among all these 8 possible values. So that's why it's 0. How about 0, 1? So here 0, 1 and 0, 1. So you can have THT or HTT. That will give you the random variable xy equal to 0, 1. So summarize all this. This is the John PDF. Double check whether all these numbers add up to 1. But in fact, before that, maybe you try to get the marginal of x add up all these numbers and add up all these numbers, all right? So this is the marginal of x. That means for a fixed x value, sum up all the probabilities with different y values. All right, so half-half, so it's 1. So yes, sum of all these x probabilities equal to 1. So similarly, you got the marginal of y. All right? So we got the joint distribution, we got the marginal of x, marginal of y, and what we are supposed to find? We are asked to find f of y given x equal to 1, right? X equal to 1. So by definition, it's equal to f of xy, all right? X equal to 1, y, and then divide by f of 1. So this is the definition. We are given that x equal to 1. It simply means that, okay, what it means is, just look at this line. Look at this. X equal to 1. All right? Then immediately you see that. All right? So when y equals 0, f10 is 0. So therefore, so you have to work out all this. 0, 1, 1, 1, 2, 1, and 3, 1. Do I have to work out 4, 1? 4, 1? Obviously not. It's not here. All right? So we know that we don't have a 4. All right? So we work out these 4 values. So f0, fy given x, when y equals 0, x equal to 1, so it's 0. So similar for the other 4. So now I summarize it in this table form. All right? So in fact, I can drop this part. All right? So this is the John PDF. All right? Sorry, not John PDF, the conditional distribution. Y given x equal to 1. So, you may also would like to work out what is this when x equal to 0. Then of course, the next question, after you work out this one, the next question is, are they the same? Are they the same? Are these two the same? The same in the sense that the range must be the same and the corresponding probabilities are the same. So you work it out. Now if they're the same, then what does it mean? I believe it's not the same. Obviously it's not the same. Why? So now look at this line. Is it possible, given x equals 0, is it possible to get y equals 0? And the answer is yes. Given x equal to 0, is it possible to get y equal 3? And the answer is no, you cannot, because the joint probability is 0. So therefore, the range already different, with different probabilities. All right. In fact, if you look at it, the answer that we just obtained, remember, it is 1 quarter, 1/2, and 1/4. The conditional distribution is 1 quarter, 1/2, 1/4, corresponding to 1, 2, and 3, which is exactly the same ratio as these 3 numbers. Of course, it must be like that. Why? Because how you get this number, you just divide each of this number by a constant, the same constant. So of course, this ratio is the same as this 3, the ratio of these 3. Then why we have to adjust it? And the reason is obvious. Does these 3 numbers or these 4 numbers add up to 1? No. The reason why we divide by 1/2 or divide by this number is to make sure that our conditional probability will add up equal to 1. All right? So now these numbers add up to 1. All right? So that's how y divide by the marginal of x. Okay. So here's another example. This time, save us some work. We are told what is the John PDF. The John PDF equal to this expression only when x equal 1, 2, 3 and y equal 1, 2, 3. All right? So, altogether, how many possible points for which the John PDF is non-zero? How many xy values such that the John PDF is non-zero? Or in other words, the John PDF is given by 1 over 36 x times y. How many of them? X takes the value 1, 2, 3. So for x equal to 1, can y equal to 1, 2, and 3? So y can be 1, can be 2, can be 3. So for each value of x, you have 3 values of y. So it's 3 value of x. Each of them has 3 values for y. So it's 3 times 3. So altogether there are 9 values for the John PDF to be non-zero. And it's given by the expression 1 over 36 x times y. So from here, what is the point x and y to make this the probability is the largest? What is the point xy? What are the values of x and y such that the probability is the largest? Obviously, you want fxy to be largest, you want x to be the largest, y to be the largest. So it will appear at the point with x equal 3 and y equal 3. That will give you the largest. The smallest probability will be x equal to 1 and y equal to 1. All right? Okay, so what we are asked to do, we have to find the margin of x and the condition of y given x. All right? Now, if we are asked to find this and this, all right, then that means it's implicitly that you are asked to find this as well. All right? This is part of this. All right? But if I don't ask this one, I ask this one, then this one no use. It won't help you to find this one. In order to compute this one, you need to know 2 things. What are the 2 things? You need to know the John PDF. And you need to divide it by the marginal of y. The margin of y. So you need these 2. All right? So just let you aware of that. Okay? So this one will help you to find this. So in other words, I can simply ask you to find this. Then you still have to find this one. Okay. So how to get margin of x? You are not okay. This one way to do it is to write it in a table form. So it may be okay, x 1, 2, 3, y 1, 2, 3. Then this is 1 over 36, this is 2 over 36, 3 over 36. Okay, you can explicitly write in a table, but you are not advised to do that. Why? Because it's too much work. And not only that, now we have only x equal 1, 2, 3 and y equal 1, 2, 3. So what happens if I tell you, okay, x equal to 1, 2, 3, 4, 5 up to 20, y is 1 up to 20, then your table is 20 by 20, so you have to evaluate 400 entries. You don't want to do that. All right, so you have to get used to how to do it mathematically. So, here, remember this is to sum the John PDF, the John probability function, all right, with the fixed x and sum over y. Sum all possible y values. And here, in this case, only 1, 2, 3. Now here you have to pay attention. So look at this. This is a general term. General term. All right? So every term, it will have 1 over 36. So it's a common factor. Not only that, because this sum is sum over y. So in other words, x is fixed also. The summation, that means every term, the 1 over 36 and the x are the same. Only the y change. Y can be 1, can be 2, can be 3. So I take out the common factors. 1 over 36 times x out as a common factor. So I just sum over y. Y summing from 1 to 2 to 3. So that means the first term is 1, the second term is 2, the third term is 3. So immediately I know that this is 6. All right? So the answer is x over 6. X over 6. So I don't have to evaluate every entry of this John distribution and then do the addition. So I know the answer is x over 6. And this is valid for x equal to 1, for x equal to 2, and for x equal to 3. Is it valid for x equal to 4? Why not? Huh? Because, in fact, I should write from the beginning saying that x equal to 1, 2, 3. Then this one, this is the John PDF. Outside this range, the John PDF is 0. So that's why it's only valid for x equal to 1, 2, 3. All right? Okay? Now, so f of x equal to 0 for other values of x. So once we got the marginal of x, then I can proceed to find the conditional distribution of y given x. All right? So remember, the conditional distribution of y given x, the random variable is y, y. All right? So x is fixed. X is fixed. But x is fixed at 1, 2, or 3. Can it be 4? And the answer is no. Why? Because we just have already get f of x4 is equal to 0, while f of x3 is equal to x over 6, right? X equal to 3, so it's 3 over 6 or half, right? Is it correct? Yeah, x over 6, all right? So I replace x equal to 3, so it's 3 over 6. So we only consider x equal 1, 2, or 3 because for this part, f of x is non-zero. All right? Then now, so in fact, I should write down from here to here, from this part, this equal sign, that means this equal to this, only when y equal to 1, 2, 3. All right. This equal to this. All right. This is the definition. It's true for all xy, so long as this is bigger than 0. Then this holds. But from here to here, all right. So now I'm substitute f of xy, the John PDF, a John probability function. So that one equal to this only when x is 1, 2, 3 and y is 1, 2, 3. But I already stated that x equal to 1, 2, 3. So I only need y to be 1, 2, or 3 in order to have this one. So for this part, x has to be 1, 2, 3. So all this is correct. So do some cancellation, it's y over 6. Y over 6. All right? So in other words, the conditional probability function for y given x, all right, so long as x equal to 1, 2, or 3, then the conditional of y given x is y over 6. So in other words, when y equal to 1, it's 1 over 6. When y equal to 2, it's 2 over 6. When y equal to 3, it's 3 over 6. When y equal to 4, it is 0. All right, outside this 1, 2, 3 range is 0. So I don't know whether you remember what I said earlier. This is supposed to be a function of x and y. How come there's no x? Yeah, this is just happens to be no x. In general, there may be a function of x. And in fact, because there are no x in the conditional distribution of y given x, so in other words, it doesn't matter whether x is 1 or 2 or 3. The behavior of y is the same. So we call this x and y are independent. Right? Independent. All right? So, I don't know, you can work it out. When I say independent, I look at it. So long as x equal to 1, 2, 3, the conditional distribution does not depend on x. So it does not rely on x. It doesn't matter whether x 1, 2, or 3. They're the same, so it's independent. But of course, the definition is like this. F of yx is equal to f of y. This is the formal definition of x and y are independent. All right, it doesn't matter what the y is. So you can check the margin of y, which I did not work it out. In fact, you look at this, the working here. This expression is symmetric about x and y. That means x and y, the row are the same, are similar. All right? It doesn't matter whether you consider. So in other words, if I replace all this x or swap the row of x and y, I replace all the x here by y. You replace x by y, replace the y by x, you replace this by x. I will still get the same thing. Of course, at the end, this is y over 6. So in other words, immediately I know that this is equal to y over 6 for y equal 1, 2, 3. Because what I'm going to do is just replace all this y, x by y, and y by x. Just do the same thing. So sometimes we don't bother to do it. But how do I know that they are the same? First of all, the John PDF, 1 over 36. So this one is not important. The other is x times y. X times y is the same as y times x, right? So it doesn't matter. So if the PDF is given as x squared y, then they are not symmetric because x squared, y is only y. So in this case it's not, but this is x plus y, x times y. So it's symmetric. And not only that, the range of x is 1, 2, 3. How about the y? The y also 1, 2, 3. So they're symmetric. All right? So if I ask you to find the marginal, so basically it will be the same, except that now you replace the x by y. So in other words, I already know that this equal to f of y given y, because f of y given y is equal to this one. So x and y are independent. We'll come back to independent later, but what I'm trying to say is that, okay, we work out the conditional. Just on top of it, after you get the answer, I can tell you that x and y are independent. Why? Because the conditional distribution is supposed to be a function of y and a function of x. That means it involves x and y. But here it does not involve any x in the expression. So what does it mean? It means when x equal to 1, you get the same conditional distribution as if x equal to 2 or x equal to 3. So it doesn't matter what the x is. You have the same thing. So that's why they're independent. All right, so here is another example, but this time it is continuous. This is the same. We have done it before. All right, find the marginal and then find the conditional. So find the marginal. So I have to specify this. All right, so integrate y from 0 to 2. Because the f of xy equal to this, only when x is between 0, 1 and y between 1 and 0, 2. All right, so when x here between 0, 1 and y between 0 and 2, the joint PDF is equal to this expression. Outside that, it is 0. So we just proceed to do the integration. And this is the after you complete the integration. So in other words, when x is between 0 and 1, the marginal of x is given by this expression. How about outside this range? Outside this range, then the joint PDF is 0. So this one replaced by 0. Then of course the answer is 0. So this is the marginal. So I believe it's better for you to write down the PDF or over the whole real line. So that, just to remind you, the PDF equal to this expression only where x is between 0 and 1. It's not valid, it's not the same. In fact, 0 outside that range. So I have just to remind you that, okay, when x is less than 0, the PDF is 0 for x. And when x is bigger than 1, the PDF again is 0. Why they are 0? Because the joint PDF is non-zero when x is not in the range of 0 and 1. Outside that, the joint PDF is 0. Let me just repeat it. So this is 0 to 1, y. All right. So the joint PDF is non-zero over this region. So when you try to get f of x, you have to integrate y. So if x is here, you try to integrate over this line. Try to sum up all the density. But on this line, the density are 0. So no matter how you do it, it's still 0. But over this x value, when you try to integrate or try to get the PDF, from minus infinity up to this point, this part, 0 density, nothing. From this part onward, also 0. But from this part to over here, there is density. So you just sum up all the density. All right? So the f of x will be non-zero over when x is within 0 and 1 for this example. Similarly, you can see that for Fy, all right? Remember, these are only the region. The density is just like a surface, like a mountain coming out from this region. So it's different height, different altitude. All right? Okay, so for f of y, the same thing. So I have for fixed y, I have to integrate, try to collect all the density. So if y is less than 0, nothing here. So no matter how you collect, it's still 0. When y is bigger than 2, it's somewhere here. When you try to collect the density, again it's 0. Only when y somewhere here, between 0 and 2, then you try to collect the density. Up to this point, no density. Beyond that, no density. But this part, you have a density. So you try to collect all the density within this part. So the marginal of y is non-zero when y is between 0 and 2. All right? That's what we do. You can see that here. So this is the answer. So for y, so I have to specify y between 0 and 2, try to integrate x, and x range from 0 to 1. These are all given in the joint density function. Outside that, it is 0. So complete the integration, it is 1/3 plus 1 over 6y. And 0 otherwise. The word otherwise is a little bit cheating, but you write it explicitly so that make sure that you understand what's going on. All right? Outside the range of 0 and 2, when y outside the range of 0 and 2, the marginal distribution of y is, or the density is 0. Okay. How about the conditional? Okay, so this is the answer for f of y. So how about the conditional distribution? Y given x. All right. Now it's logical to write like this. Y given x. So I write down, I define the region for which the following computations are valid. So I specify that only when x between 0 and 1. Then what I've done is valid. So for the range x between 0 and 1, I take the ratio of the John distribution with the marginal. So like that. This is the John distribution, this is the marginal. And this only valid when y is between 0 and 2. Why is that so? We need this in order this is valid. So in other words, this goes to this one only when y is between 0 and 2. This part is valid. This equal to this is valid because we already specified that x has to be between 0 and 1. Oh, sorry. This one equal to this is, you need these two conditions. You need these two. Define both x and y. All right? So simplified it, and you got this one. So now you can see that the conditional distribution of y given x is a function of x and y. It depends on x, depends on y. All right? So what happens if x equal to 1? All right? Then x equal to 1. So what we do is that, okay, when x equal to 1, it satisfies this range. So I substitute x equal to 1. So it is 3 times 1 plus y over 3 times 1 plus 1. All right? So it is 3 plus y over 8 for y between 0 and 2. So that is the the conditional distribution of y. Okay? Y will equal to this one, equal to this expression, so long as y is between 0 and 2. And this is for x equal to 1. Now when x equal to, let's say, 0.5 or half, when x equal to 0.5, then this is 3, so we are looking at f of y given x when x equal to 0.5. Then this is equal to 3 times 0.5 plus y over 2 times 3 times 0.5 plus 1, which is 1.5 plus y divided by 1.5, 2.5 over 5. All right? Or 3 plus 2y over 10. Right? So this is only valid when y is between 0 and 2. So my point is, when x equal to 0.5, you substitute x equal to 0.5. Then you get the density. It's equal to 3 plus 2y over 10. Again, it depends on y. So long as y is between 0 and 2. But when x equal to 1, you have a different expression. So how y behaves, how the density behaves for y, for given x, all right, it's given by that expression, so you can substitute the x value to get the to get the condition of y for that particular x value. This is just a general form. Okay, a general form for any x between 0 and 1. So in particular, if you are given the x value, let's say x equal 1/4, then you substitute x equal 1/4 and see how it behaves, how y behaves. All right, so here it is. So 0.5 is equal to this. So they are not the same. All right? So we can work out the y given x. All right? So it's the same thing. All right? So so when y is between 0 and 2, So log of x is between 0 and 1, then this is the conditional distribution of x given y. And here I take some example. If y equal to 1, I substitute y equal 1. So that is the expression. If y equal to 0.5, then I got this. And they are not the same. They are not the same. All right. So, yeah. Okay, to summarize all this, you just have to remember, first of all, if you are given the John probability function or John probability density function, it tells you everything. From there, you can work out the marginal of x, how x behaves. All right? How y behaves. Then there's another question. So what happens if you are told about something about the x, let's say x equal to a certain value, then how y will behave? So we have to find the conditional distribution of y given x. Similarly, you can talk about conditional distribution of x given y. Given y equal to a particular value, especially the conditional distribution. You have to understand, when we say conditional distribution like this, you have to know the definition, of course. But you also have to understand this referring to one random variable, and the random variable is y. All right? X, in this case x. X. And this one is also a random variable, x. But they are, in general, they are two different distributions. They can be the same if x and y are independent random variables. If not, in general, they are not, unless you prove it. All right, they're not, then these two are different. So the first one is that we don't care about the y. All right, and then we just look at how x behave in general. X take this value with that probability density and so on. But the conditional probability density is different. So we look at, if you are told y equal to a certain value, the little y, then how this random variable x behaves. Now, but the expression itself, this one, so equal to something, that thing, that expression will involve x and y, involve both x and y in general, all right? But in some of my examples, it just depends on x. So in that case, it's a special case. X and y are independent. That's why you don't see y there. But in general, it should be a function of x and y. All right? But since although it's a function of x, y, but you must understand that y, in this expression, the y is constant, fixed. Only x is the random variable. All right? X is the random variable. So this little x is the value of this random variable. While y is fixed, you cannot change the y. Y is fixed at this particular value. All right? So that's what I want you to make clear. And also, whenever you talk about John distribution, marginal distribution, or conditional distribution, always remember to mention about the range for which the expression of the probability function or probability density functions is valid. All right? Outside that region, outside that range or area, it is 0. Sometimes it's cover the whole real line or cover the whole R square. Fine. But if not, then you have to remember that outside that region or outside that range, it is 0. Okay, so I think I stop here and see you after 1 week break. And remember, October 5th, you have your midterm test. It covers up to this chapter, up to section 2. Which already finished, all right? So that's the John distribution. The conditional distribution, the marginal distribution is beyond section 2, so it will not be covered in the midterm test.